Hello and welcome to our channel again. So I am Suraj with a new video of mine where I'll discuss about the derivation of one of the Maxwell equations. So you know that what's actually the Maxwell equations is. So I will make a video on the detailed analysis of the Maxwell equations, that exactly how Maxwell equations proved. There are almost four Maxwell equations. So in this video, we are going to discuss about one of the Maxwell equations and its derivations. Actually, to know more about the Maxwell equations, you have to deep dive into the electromagnetism, electromagnetic inductance, and all that things. So maybe in the future, I will make a video on the electromagnetic inductance and waves so that you can understand that how the Maxwell equation shapes our electromagnetism. So for now, we are only restricted to the derivations of our one of the Maxwell equations, which we are going to write here. So we can start our video now. So this is the Maxwell equation that we are going to prove. Okay. So as you can see here, we have done the line integral of the electric field, and it is equals to the negative of the rate of change of the magnetic flux. So what this is? So this is the very important formula, and it is also very important in the electromagnetic inductance. So we are not going to deal with a very detail about what this thing is maybe in the future videos, but I am going to quick recap of this particular formula, that what it is saying. So the formula is that here, first of all, you have to understand the right hand side of this particular formula. So the right hand side is saying that if there is a magnetic flux which is changing over a period of time, this can be equals to the line integral of the electric field. Okay, so first of all, this formula does not makes much more sense. So we are going to write in a much more better form. So the Faraday's law tells us that if there is a some sort of let's say there is a coil here. Okay, so if there is a coil, okay, a circular coil is there, and if there is any type of the magnetic source, let's say it is a magnetic material, I will say that it is a magnet, let's say it is a bar magnet here. So if this is a bar magnet, okay, let me draw it much more clear way. Oh, so bar magnet. Okay, so this is our bar magnet. It is north pole and south pole. Okay, whatever this is. So the thing is that it is at rest. It means there are the electric field lines, sorry, magnetic field lines that are emitting out of this particular magnetic material, and this is a coil. So what we experimentally prove that whenever there is a relative motion between these two particular, let's say this is A and this is the B, okay? So whenever there is a relative motion between these two particular, it means the relative, if there's relative motion between them is not equals to zero, if the relative motion between them is not equals to zero, it means there is a current in that particular coil flowing, known as the induced current due to the induced EMF. So what I am saying, so let's understand in a simple manner. So what happens is that whenever you try to move the magnet in whichever direction, by changing the magnets, by moving the magnet, and there is a change in the magnetic flux, there is a changing in magnetic flux also relates this particular formula. Okay, so first of all here, carefully analyzing, what we gain is that whenever we move our conducting material, whether our coil, whether our this particular magnetic material, there is a current which is flowing in this particular coil, known as the induced current, and the EMF that is produced is known as the induced EMF, because you know that EMF is the responsible for the continuations of the flow of the current in a particular circuit. Okay, so it means there is a current that is flowing. So what this is, why the moving magnet, or whenever you move this particular conductor or this particular magnet, there is a current, induced current, and that's what the Faraday see. And he relates that the induced EMF is equals to the negative of the d by dt of our this particular quantity known as the magnetic flux. So magnetic flux is nothing. Magnetic flux is nothing. Okay. So I will quick recap here that magnetic flux is generally the number of electric field, magnetic field lines. It means the number of magnetic field lines passing through a area. It means it can be written as the integral of a BdA. It means how much electric field line is passing through a given area. Let's say I have imagined that this is our area. Okay, so if this is our area, how many magnetic fields lines are passing through that particular area is what known as our magnetic flux. So if there is a change in the magnetic flux, there is a induced EMF produced in this particular circuit, and there is a flow of current, induced current. So this is the thing that Faraday's relates, and he gave out this particular very important formula that E is equal. E means this induced EMF. You have studied what EMF is not. I will make a video on explaining the EMF because EMF is very important. Okay, so the induced EMF is produced when the magnetic field, or we can say that conductor is moving in a magnetic field, or you just move a particular magnetic material. There is a flow of the current known as the induced current by this phenomena. By this phenomenon, there is a movement of this induced current. Even there is no any source of, you can say, there is no any external source that you can imagine that there is a flow of the current here. It means that the magnetic field is responsible. You can say the change in the magnetic flux is responsible for this induced EMF, and this induced EMF is producing the induced currents. So now we are going deep into the derivation, that you know that the induced EMF is equals to the negative of the d by dt of this particular magnetic flux if the magnetic flux is changing. And you can imagine that if B is constant, then the differentiation is equal to the zero. It means there is no any type of the induced EMF, you can say. It means suppose that they both are at rest, A and B both are at rest. It means there is no any induced EMF. And that's the situation practically. But when both, any of them starts moving, then there is a sun, and anyway it starts moving, then we see that there is induced current that is produced. So there is a various methods to just producing the induced EMF. So this is not the scope of our video. Our scope of video is to prove this particular equation. So can we write that E is equal to the negative of means the induced EMF is equal to the negative of the magnetic flux with respect to the time differentiation? Okay, so let's move forward to our derivation. So what we can write it as, what we can write is that, first of all, on the right hand side, I want to tell you that on the right hand side, you have seen here that it is electric field. And you have studied that the line integral of the electric field is not equals to the zero. It means the electrostatic force is a conservative force. It means electric field's line integral is equal to the zero over a closed path, and that we prove down. It means that we studied basically that the line integral of the EDL is equals to the zero. But what is happening here? What is happening here? Why it's not zero? Okay, so why it's not zero? Because here E in the expression, okay, in this expression E, I'm telling, okay, so let's keep it apart. In this expression, E is equals to the EC plus EN. Okay, so what I have now written, remember that the E in this particular Maxwell equation is not the electric field that is produced by the static electric charges. Electric field E in this particular expression is the combination of our EC, which is the conservative electrostatic force electric field, plus EN. What is EN? So here EN is responsible for all of these things. En is what known as the induced electric field, short form. Okay, induced electric field. This is what the En means. What is induced electric field? So I have told you that whenever a particular, you can say that whenever this particular magnet starts moving, it's create the electric field. It means the moving magnetic material, maybe a magnet, you can say, that can produces the electric field known as the induced electric field, which is non-conservative in nature, That's why you can see that here it is not equals to zero, because here E is not C. Here E is the combination of our conservative force electric field plus the induced electric field, which is produces by whenever a magnet moves, and whenever a magnetic substance starts moving, it's created the electric field. You have studied that the moving charges created magnetic field, just like the moving magnets created the electric field. So you know that there is a very deep meaning behind this, which can be proved out by the relativity. Whenever I start the advanced series on the relativity, you will see that how electromagnetism works in the relativity. How the moving charges how the moving charges created magnetic field is really they created the magnetic field. So there is a lots of things there which is very fundamental, and there is a very good proof of these types of things in the Einstein's relativity. Okay, so I am talking about out of the scope. So now let's return to our topic here to prove our this expression. So here I will clarify you that E is the collections of EC plus En, where En is the induced electric field which is created when a particular moving magnetic substance, okay, by the moving magnetic substance. Okay, so now let's move towards the proof. I have written that E is equals to the negative of d by dt of the magnetic flux. Okay, so now what we can write is that what we can write is the non-electrostatic. Okay, you know that this E is known as the induced EMF. Okay, so this is induced EMF. So how we can write it like this is that, are you thinking that the induced EMF is generally responsible for the flow of currents? Whenever you study the battery here, the EMF is very important, because EMF is what that generally moves the electrons from the positive to the negative terminal, so that there is a flow of current forever. So we can write that E can be written as the integral, closed integral of the ETL. You know that this first Maxwell equation, I think this is first or the second Maxwell equation. This is very easy to prove by the simple. Mainly the third and the fourth Maxwell equations are very important. And this proofs is also quite hard. So this Maxwell equations can be written as that induced electromagnetic, as you can see here in a formula that I will, yeah, the formula is, the formula is that V, which is change in V, can be written as negative of the integral of the EDL, of the EDL. Can we write it like this? Yeah, we can write it like this. But here E is the conservative field. But here E is not the conservative field. E contains both conservative and the induced electric field. So here E is the collection of both. So you can't write E as EC. So this is just an alternative formula of this particular induced EMF. So can we put down the value of E in this equation? So while putting the value of E in this equation, this is a very simple derivation that the line integral of E dl can be written as the negative of the d by dt, as the negative, okay, as the negative of the d, negative of the d by dt of our magnetic flux. So this is a very simple derivation which you can use. Okay, this doesn't require any type of the very complex derivation. You can generally say that the induced EMF can be written as the line integral of the EDL, because you know this can be proven by the solenoid. Okay, so I think no, this can be okay. I will prove this, that how the EMF is equals to the line integral of the EDL, where E is not equals to the our normal electric electric field. Okay, how you can say that this is true? So this can be true by using the solenoid. So I will tell you. Okay, finally I can tell you that suppose that there is a solenoid. You know what solenoid is? It means you just do this stuff, you just wrap a coil around this. Okay, you just I think, okay, you just wrap the coil around like this, just like this is the typical thing that we can do about. Okay, suppose that this is our solenoid which contains some n number of turns, and you know that the strength of the magnetic field the produced by the solenoid is directly proportional to its end, which is the number of turns. So if there is a some sort of like this thing, okay, and what happen is that you put down it in a some, you just flow out a current, okay. What happening is that you are just supplying it some sort of current, but there is no any type of the external circuits here. Then how it is flowing? You keep it in a magnetic field B, okay. So you keep it in a magnetic field B. So if you keep it in a magnetic field B, and what you find is that, and you just change the magnetic flux, you are just changing the magnetic flux. Suppose that it's kept in a magnetic field B and you are changing the magnetic flux, what you will see is that there is a current flow here, okay. So there is a flow of current, but what we found is there is no any external type of circuits that is doing this flow of current. Then how the current is flowing here if there is no any type of the circuits? What we found is that, again by the Faraday's law, there is a electric field present. Yes, there is electric field, but this is not the electrostatic electric field that is generally responsible for the flow of currents. It's the induced electric field which is produced by this magnetic field change, say that change in the flux, okay. So change in the magnetic flux is what responsible for the producing of the En, which is the induced electric field, and which is responsible for the flow of current. Now you understand that why if we just changing the flux can lead to the flow of currents, because the magnetic field which is moving magnetic, when you just move a magnetic material, what is happening is that there is a induced electric field which is produced by the magnetic substance, and that is what responsible for the flow of currents in a solenoid. The flow of currents in the solenoid, and that's what it is responsible. Now we understand, yes, this is the true and the real observations. So can we put that the electromotive force is equals to the line integral of the EDL, just like we put down like this? But here is the electrostatic, but here the E is not the electrostatics. Here is the induced, or the collection of the conservative or the induced electric field. And now we can just substitute our thing and we get the formula. So this is the basic derivation of our Maxwell equation. And you know that it is very easy to prove. We don't have to do any type of the complex thing. We just relate it by a very simple relationship, and we just do this particular formula. So this is the video where I explain the Maxwell equations. You know that Maxwell equation is a very complex, so it requires some more videos for a real understanding of the things. In this video, I have not given about all of the things in the Maxwell equations because it will be a very long video and I want to make a short video. In the next video, maybe I will explain a detailed concepts in the Maxwell equations, and which requires some of the electricity backgrounds, which is not generally taught in class 10th. So I will start a series on some electric chapters, then we will start the Maxwell equations. And after starting, you can know about that how this in Maxwell's proved these very beautiful equations, how the time varying magnetic flux created the electric field, induced electric field, and all that things. So this is the video of mine on the Maxwell equations, and I know that this video is not quite very lengthy video. It contains a very short concepts. Maybe in the next video I will try my best to just explore you some of the animations through which you can understand the Maxwell equations in much more better way. So thank you for watching my